So we have already seen the master theorem for both the cases. First case is when a constant is getting subtracted from n, and second case is when n is divided by a constant. So in both the cases, n is getting reduced. The general recurrence in the first case is t of n is equal to a times t of n minus b plus fn, where fn is some function of n. In this case, we just check the value of a and compare it with 1. If a is equal to 1, then the answer is n times fn. If a is less than 1, then the answer is only fn. And if a is greater than 1, then the answer is a to the power n by b into fn. So either we keep the fn as it is, or we multiply n with fn, or we multiply a raised to the power n by b with fn, depending on whether a is less than 1, equal to 1, or greater than 1. The second type of general recurrences are Tn is equal to a times t of n by b plus fn, and here fn is given in the form of n raised to the power k log n raised to the power p. So fn may have a component of n and fn may have a component of log n. There are four constants here, a, b, k and p. So first we find log of a to the base b and then compare it with k. There are three possibilities. Log of a to the base b is greater than k, we call it case 1. Log of a to the base b is equal to k, we call it case 2. And log of a to the base b is less than k, we call it case 3. In the first case, the answer is n raised to the power log of a to the base b. So we have already computed log of a to the base b because that is what we are comparing k with. Just do an n raised to the power that number, which means n raised to the power log of a to the base b. In the second case, where log of a to the base b is equal to k, we check the value of p. P is the power of logarithmic component in the function fn. If p is equal to minus 1, which means that the logarithmic component in the function is in the denominator and it is only log n. Fn has a log n in the denominator, then we say that the answer is n raised to the power k log of n. If fn is in the denominator and the power is greater than 1, which means that in the denominator we may have log square n, then the answer will be n raised to the power k, which means that in the fn we will ignore the logarithmic component. And if p is greater than minus 1, which means that either the logarithmic component is not present, or if it is present in the numerator. In that case, we will just multiply fn with log n. Therefore, if you do not have any logarithmic component in the denominator, just multiply function with log n. If you have only one power of logarithmic log n in the denominator, then multiply n raised to the power k with log of log n. And if you have a higher power in the denominator, then just ignore the logarithmic component and the answer is only n raised to the power k. This is the second case. Third case is when log of a to the base b is less than k. Again, we check the value of p. If p is greater than or equal to 0, then answer is function itself. And if p is less than 0, which means that you have the denominator, you have the logarithmic component in the denominator, then answer is only n raised to the power k. You ignore the logarithmic component. So this is a quick recap of the master theorem. Now let's take some examples. Let's look at the first question. The first question is Tn is equal to t of n by 2. Tn is equal to t of n by 2 plus 1. Here n is getting divided by a constant. Therefore, this case will be applicable. In this case, a is 1, b is 2, k is 0 because n raised to the power 0 is 1 and p is also 0. We find log of a to the base b, which is log of 1 to the base 2. That comes out to be 0. K is also equal to 0. So log of a to the base b is equal to k, which means that this is the second case. This case. So let's number it 1, 2 and 3. So this is the second case. In the second case, we check the value of p. Because there is no log n in the denominator, therefore the answer is Tn is equal to Fn into log n, which means 1 into log n, which is log of n. Here also n is getting divided by a constant. So this is also this case. In this case, a is 2, b is 2, k is 1 and p is 0 because we do not have any logarithm component in the function. Now log of a to the base b is log of 2 to the base 2, that comes out to be 1. Because log of a to the base b is also 1 and k is also 1, this is also case 2. And we know that in case 2, we check the value of p. Because we do not have any logarithmic component in the denominator, therefore the answer is this function into log n. The answer is n log n. I know that we have already discussed these questions in the previous video, but this is for a quick recap. Consider the next question. In this case also, a is 3, b is 3, which means that log of a to the base b will be 1. Log of 3 to the base 3 is 1. And because k is also 1, so this is also second case. And because there is no logarithmic component in the denominator, therefore the answer in this case is also Tn is equal to n times log of n. In the previous case, where Tn was 2Tn by 2 plus n, the answer was n log n, and in this case also the answer is n log n. Remember, we are talking about the asymptotic complexities and not the absolute equations. The constant factor of these two equations will be different, but in terms of asymptotic notations, both of them are theta of n log n. Next question. Here a is 2 and b is also 2. Therefore, log of a to the base b will be 1. Log of 2 to the base 2 is 1. But because power of n is 1 by 2, therefore k is equal to 1 by 2. Now log of a to the base b is greater than k. This is the first case. And we know that in the first case, the answer is Tn is equal to n raised to the power log of a to the base b, which means n raised to the power this component, which is 1. The answer is big O or theta of n. Consider this question. Here n is getting decreased by a constant and not divided by a constant. When n is getting decreased by a constant, then it's the first equation. In the first equation, we only find the value of a. Here the value of a is 2 and 2 is greater than 1. If 2 is greater than 1, then answer is Tn is equal to a raised to the power n by b into function of n. Function of n is 1, fn is 1. Therefore, the answer is a raised to the power n by b. A is 2, 2 raised to the power n by b. b is 1. Therefore, the answer is 2 raised to the power n. So, this is an exponential complexity. Now, this is a tricky one because neither a constant is getting subtracted from n nor n is getting divided by a constant. Here, n is getting reduced, but the reduction is square root of n. So when we first call the function for n, then from inside the function will be called for square root of n. Therefore, the reduction is not like the first equation or the second equation. The reduction is in terms of square root. In such a case, we have to make this equation like the second equation. How do you make this equation like the second equation? We change the function Tn. Let us assume that T of n is equal to S of k, such that n is equal to 2 raised to the power k, or k is equal to log of n to the base 2. In this equation, if we replace n with k, we will get t of 2 raised to the power k is equal to t of, this is n raised to the power 1 by 2. So n is 2 raised to the power k, so this will be 2 raised to the power k by 2. We know that Tn is equal to S of k. So this comes out to be S of k is equal to S of k by 2 plus 1. Now this equation is similar to this kind of equation where the reduction of the variable is in terms of division by the constant. Therefore, we can say that S of k is equal to log of k. S of k is equal to big O of log of k. This implies that T of n, because S of k is T of n, S of T of n is equal to log of n, because k is log n. So this is the final answer of the equation, that Tn is equal to theta of log n. Consider the next question. In the next question, a is 2, b is 2. So log of a to the base b will be 1. Log of 2 to the base 2 is 1. And k in this case is 3. Therefore, log of a to the base b is clearly less than k. If it is less than k, then we are in the third case. So in the third case, we find the value of p in the function. Because log n is coming in the denominator, therefore value of p is minus 1. And if value of p is minus 1, then Tn is equal to big O of n raised to the power k, which means that we will ignore the logarithmic component. In this case, Tn will be big O of n raised to the power 3. How about this question? In this case, Tn is equal to 2Tn minus 1 plus n. This is the first kind of equation where a is 2. So a is 2 means that this case, then answer is Tn is equal to order of a raised to the power n by b into Fn. Fn is n, b is 1, a is 2. So this is big O of 2 raised to the power n into n. That's it. What if the equation is simply Tn is equal to n raised to the power 4? It essentially means that this is not a recursive function because Tn is not defined in terms of T of n minus b or T of n divided by b. If this is not a recursive function, it means that the function is called only once. And if the function is called only once, the function takes n raised to the power 4 time. This means that the function is big O or theta of n raised to the power 4. So these two recurrence equations make sense only when the function is calling itself. So when Tn is calling itself with a reduced value of n, this reduction can be in terms of subtraction or division. Either a constant is getting subtracted from n or n is getting divided by a constant. But if the function is not getting called recursively, then the recurrence equations does not make sense. Let's say the equation given to you is like this. In this case, a is 2, b is 2. Therefore, log of a to the base b is 1. Log of 2 to the base 2 is 1. And k is also 1. Therefore, this is the second case. In the second case, we check the value of p. In this case, what is the value of p? The value of p is 1 because log n is in the numerator. And we know that if log n is in the numerator, then we just multiply this function with log n. Therefore, Tn is equal to this entire function, which means n times log of n into one more log n. So this is just Fn into log n. I know that master theorem looks bulky and it can be really intimidating, but you must remember that even though it is lengthy, it is not that difficult. Let me leave you with one question. How will you solve this recurrence? Tn is equal to 4t square root of n plus log square n. This is for you to solve.